Hello, my name is Parker Stewart and I go to Sayre School.
My name is Jackson Gabbard and I go to Paul Lawrence Dunbar, MSTC.
And we're both in the class of 2021.
And recently we collaborated to create this solar tracker. We are making this video now to walk you through the process that we have been through to create this solar tracker.
As the market for renewable energy has increased, the solar industry has exploded. But there is a crucial problem with solar. It's only good at certain hours of the day because it's often in a fixed position. As a result, solar tracking companies have become very popular. But these units are often very expensive, often very far out of the purchasing power of the average day consumer.
So our idea was to make a solar tracker that was both sustainable but still as efficient as these market-ready solar trackers.
Our original idea was to have two light sensors mounted on the panel that would compare values into a Raspberry Pi. The idea was that if the panel is not at the right angle, with a divider in between, one of the light sensors would have a shadow on it, and then it would read lower values into the computer. The computer would then move the panel until both sensors got about the same amount of sunlight, meaning the panel is facing directly at the light source.
But these light sensors were very inconsistent and unreliable. So we moved to something that would not use a sensor, this being a GPS tracking system. This system used the azimuth value, which is the north and south angular distance from the horizon that the sun follows as it moves across the sky, to control the computer to make the panel move across with the sun.
But our original azimuth following GPS system was not good enough. What we needed was trying to get the panel as close to 90 degrees from the light source as possible. As a result, we used the angle of inclination using various solar geometry angles to find the best angle possible. To find the current angle of the panel, originally we used a gyroscope sensor that would read it back into our original program. But this sensor did not work very well and kept getting corroded from the elements. As a result, we started timing how long it took the panel to move from one position to the next. We then put these into our program and then we would run the program for that long to move it to the next position. In order to control the massive weight of the panels, we used a crossbeam, which is longer on the ends where the panels are extending, but shorter this way. This distributes the weight evenly among the panel. We also cut our support beam at 60 degrees as a good starting angle, which the panel can then move from there. In order to allow our panel to move, we used industrial door hinges, which allowed us to achieve almost 90-degree angle of freedom.
Our computing system was all held on a Raspberry Pi, which we mounted to the back of the solar tracker. Using relays, we controlled this outdoor linear actuator to extend the panel up and down.
Because we don't want to flip the wires back and forth manually, we made a double pull, double throw relay system. So if this top relay is activated, the polarity is positive and the actuator is able to extend. But if the bottom relay is activated, the polarity is negative and the actuator retracts.
Using this solar charge controller hooked up in a parallel configuration, we were able to track measurements of voltage and amperage to eventually determine how many watts our solar panels were producing at one time. After many months of perseverance through 2 SD cards breaking, 1 computer breaking, and a complete electrical and battery flooding, we were finally able to take data with our solar tracker and compare it to a stationary panel elsewhere in Lexington. After graphing out the 40-some data points that we were able to get, we were able to see a consistent wattage generation throughout the day, which is exactly what we wanted to see with a solar tracker.
We were super excited about this result, and we compared our graphs to some of the stationary panels we have in Lexington, and to our surprise, we were able to achieve 35% more production than the stationary panels. This beats industry averages.
In the future with this project, we'd like to take a lot more data points and try to determine correlations between weather and the effectiveness of our solar tracker.
Thanks for watching.